All right, let's try this again. So today we are going to be learning about how to calculate the work done by a constant force on an object. All right. In doing that, it will be necessary to learn a little bit about the dot product. Okay. So I guess let's start here. So hopefully from last year you remember that when you do work on a thing, what you're doing is you're changing the energy in some way, right? Like if I do work on this calculator, I can change the amount of gravitational potential energy it has. I can change its kinetic energy, right? But in all of those scenarios, I'm doing work and in some fashion changing the energy of the calculator, all right? We are going to focus next chapter a little bit on how work affects the energy, okay? What we're going to focus on this chapter is not so much how it changes the energy, but how work is done and how to calculate the work, okay? So a couple things about work. So like I just said, work basically changes the energy in some way, okay? All of this stuff down here is about how the energy changes. For the purposes of this chapter, here's what you need to know, is this stuff here in yellow. All right, this is supposed to be me highlighting, not crossing out, okay? So in order for a force to do work on an object, there are two conditions. One, the object has to be moving, okay? If the object is not moving, no matter how tired you get, you are not doing work, all right? Secondly, the direction of the force can't be perpendicular to the motion, all right? At least some component of the force has to be either working with or against the motion, all right? So if your displacement is this way, if your force is perpendicular to it, that force is not doing work, okay? And I guess I probably should have included this here in yellow, oops, in my highlighting, sorry, which is this last part. The work is always going to be negative if the force is somehow working against the object's motion, and then obviously it's positive if it's working with the motion, okay? So that's kind of in a quick nutshell what work is, all right? And so last year we learned that you could calculate the work by multiplying the force by the displacement times the cosine of the angle between those two vectors. So a couple quick comments about this equation. When you use this equation, notice there are no arrowheads in this equation. So that means we do not use positive and negative signs when we use this equation, okay? And your angle is the angle between, I'm having trouble with my tablet today, so I'm writing at a weird angle. You know what, I'm going to bite the bullet, and we're just going to put it down like this, and hopefully it'll work. Okay, so theta is the angle between your force vector and your displacement vector drawn head to tail. In fact, that's an important thing. Actually, sorry, trying to write one thing and say another. That doesn't work. So anytime you look for the angle between two vectors, you always draw them head to tail. Okay, so if this is your force vector and this is your displacement vector, then to find the angle between them, you do not place them head to tail, like you do when you add vectors, all right? So this would not be the angle. That's not what we're looking for, okay? What we want to find is the angle between them drawn, how about if I do this right? It's the angle between the force and the displacement vectors when they're drawn tail to tail. Okay, so not like the way I have it drawn. What you want to do is place them tail to tail, and so now this is the angle that you're looking for. Okay? All right, so I did a rotten job explaining that. Angle between two vectors, you draw the vectors tail to tail. Okay, that will be important. All right? Okay, so last year we learned some sort of special cases of this, right? And those three special cases are if the force and displacement are parallel, anti-parallel, or perpendicular. Then there are some easy things to do. Okay, so let's talk about parallel. So here we've got a box sliding to the right, and Roy pushes it to the right. Okay, so here's the deal. So here's my box. The problem tells us that the force of Roy is 40 newtons. 40 newtons. And it tells us that it's going to slide to the right 3 meters. So here's my displacement vector. Okay? So in this instance, you can just simply multiply 40 times 3 to get the work. Okay? Why? Well, so if we use the original equation that I gave you, work. Oh, so to be clear here, when you calculate work, you're finding the work done by a force, a specific force. So here we're interested in the work Roy does. So to calculate the work of Roy, I'm going to multiply the force of Roy times the displacement times the cosine of the angle between those. Well, both my force and my displacement are this way, so the angle between them is 0. So this just becomes 40 newtons times 3 meters times the cosine of 0 degrees. Cosine of 0 is 1. 40 newtons times 3 meters times 1 gives you 120 newton meters, which you may remember is the same as 120 joules. Note the spelling on it. And that is the same as 120 joules. Okay, so if your force and displacement are parallel, you can just multiply the magnitudes of those two numbers. All right. Now, if, on the other hand, the object was moving forward and Roy tried to slow it down, so we're going to use the same displacement vector, but now Roy is working against it, right? Because it says he's pushing to the left. So here we go. So here's our force of Roy, 40 newtons, right? I guess you could call it negative if you wanted, right? So now you're still going to multiply, but you know the work has to be negative because now my force is working against my displacement. So it's got to be negative 120 joules, all right? Mathematically, it's work of Roy equals force of Roy times displacement times the cosine of theta. So my force of Roy is 40 newtons. Remember, no positive and negatives when you use this equation. Times my displacement, 3 meters, times the cosine of the angle between them. Well, my displacement is this way, my force is that way, the angle between them is 180 degrees. My arms don't bend that way. Cosine of 180 is negative 1, right? So this is going to give me 40 times 3, which is negative 1. So you get negative 120 joules. Or you can just do it more simply and just go, well, I know they're anti-parallel, so it's just negative 40 newtons times 3 meters gives you negative 120 joules. All right? So really quickly, in general, what you should think about is, notice here, this was positive 120 joules. That usually is going to represent some sort of gain in energy. Actually, do you know what? That's not always true. There's one exception, okay? So I'll come back to what that exception is when we get to chapter 8. But in general, usually positive work means positive change of energy, with an exception, all right? Here we've got negative, so we're losing energy. I'm going to back off on stressing that. So Marie will confuse it later on. All right. So here, notice our force was working with our displacement, so that was positive work. Here, our force was working against our displacement, so that's negative work. Here, we've got an object, 5 kilograms. It's sliding to the right, so let's go ahead and draw on that displacement vector again. It says, how much work does the normal force do? Oh, well, let's see. So my gravity is 5 times 9.8, negative 49 newtons. My normal force is positive 49 newtons. So notice now my displacement is this way, and my force is perpendicular to it. So it's neither contributing to nor working against the motion. It's like right in between, right? Can you guys see me? Yes. Okay. So the work should be 0. Mathematically, it's this. The work of the normal force equals the force of the normal force times our displacement times the cosine of the angle between them. So I'm going to get 49 newtons worth of normal force, 3 meters worth of displacement times the cosine of 90 degrees. Cosine of 90 is 0, so you're going to get 0. Okay? So, anytime your force is perpendicular to your displacement, that force does not do work. Okay? That doesn't mean that other forces might do work. It doesn't mean that other forces might do work, but the normal force in this example does not. And similarly, gravity also will not do work for the same reason. Okay, so that is what, back here, when I kind of talked through the important points about work, the direction of the force can't be perpendicular to the direction of motion. Okay? All right. So after some hemming and hawing and realizing that my video is going to be too long, I'm going to skip example 4 because I think we did stuff like this last year in honors. And I think that if you follow example 5, you will understand what's going on here. All right? So at some point, it might be worth your while to go back and recalculate to do number 4 if you want, as a little bit of extra practice. Okay? And I'll give you the answers right now real quick so you can check your work if you decide to do this later on. All right? So you're trying to calculate the work done by a couple different forces. And really, ideally, I would like you to do it sort of as many ways as you can. In a minute, I'm going to show you 3 different ways to calculate work. And ideally, you ought to be able to calculate the work done by each of these forces, each of those 3 different ways. Okay? So I'll get to what those are in a minute. So question A says, how much work did Roy do? That ends up being 2,078 joules. The work done by friction ends up being negative 1,035 joules. The work done by the normal force, spoiler alert, is 0. And then the net work you can calculate 2 ways. I will talk about this later on. There are 2 ways you can calculate the net work. But regardless of which way you do it, you end up getting 1,043 joules is the net work. Okay? All right, so let's do example 5 because I think it really drives home an important point. All right? So before we do example 5, check it out. There are 4 ways to find work done by a force. Okay? Option number 1 is to use the equation that we've been using. Work done by a force is equal to the magnitude of the force times the displacement times the cosine of the angle between those 2 vectors. Don't just write down the equation. Make sure you know what the things are, okay? And as a reminder, you do not use positives or negatives, okay? Now, option number 2, sometimes it's easier to split your force into components or to think about the components of the force, all right? And so then what you do is to calculate your work, what you do is you split your force up into components, and what you're interested in is the component of the force that is parallel. Okay? Parallel to what? Parallel to the displacement. Okay? So this represents the component of the force that is parallel to the displacement. So you're going to multiply that by the displacement vector, and here you have to use positives and negatives. Okay? Basically what you're doing is you're figuring out, all right, my displacement is this way, my force is this way, how much of this force is working against my motion, okay? All right, now the third option is, instead of splitting your force up into components, sometimes you want to split your displacement up into components, okay? So you're going to go work is whatever my force is times the component of my displacement, which is parallel to the force, okay? So you split the displacement vector up into components. Whichever component is parallel to the force, that's the one you want, and then you multiply. And again, you've got to use your positive and negative signs. All right? Option number 4, coming soon to a physics video near you. It's actually at the end of this video, so hang in there. All right? So we'll get to number 4 in a minute. All right? So let's do an example so you can kind of see this. All right? So in this one, we've got a ramp, and I'm actually going to change this example. So it says a 50-kilogram box of donuts sits at rest at the top of a frictionless ramp, incline. No, I'm not going to give you the angle. sits at the top of a frictionless ramp. Ooh, I re-recorded this video. I'm glad I did because I had forgotten that. That didn't make sense. All right, so a 50 kilogram box of donuts sits at rest at the top of a frictionless ramp. The ramp is 5 meters long and 3 meters tall. Okay, how much work does gravity do? How much work did the normal force do? What's the net work? Okay, so here we go. Let's make a drawing. So our ramp is going to look like this. It is going to be 3 meters tall. It is going to be 5 meters long. I guess you could really quickly, I don't want to put this 5 there. Where do I want to put it? I don't know. 5 meters. You could, if you wanted to, you could figure out that this guy here is 4 meters, although we're not going to need that for the drawing, for the problem. All right, so let's make our drawing here. So we've got a 50 kilogram box, 50 kilograms. All right, and what forces act on it? Well, there's gravity. That's going to be 50 times 9.8, so that's going to be 490 newtons down. And then there's going to be a normal force going this way. And then let's go ahead and draw in our displacement vector. Our displacement vector is 5 meters this way. Hey, Sally. Okay, so question A says, how much work did gravity do? So I'm going to... So A, the work done by gravity equals what? All right, so I'm going to do it using each of those 3 methods that I just showed you. So option 1 would be, well, the work done by gravity. Oh, no. Come on. I'm just trying to resize my screen. There we go. The work done by gravity is, well, force of gravity times displacement times the cosine of the angle between those 2 vectors. So my force of gravity, I already know, it's 490. My displacement, I know, it is 5 meters times the cosine of some angle. Cosine of some angle. And remember, that angle is the angle between our force and our displacement vectors. Okay? So, let's see. I think the angle I want is this one here, right? The angle between my force vector and my displacement vector. So it's 5, 3. I want this angle, right? Because the force is vertical, just like the 3 meters, and the 5 meters is along the ramp. So I want that angle. So if that is a right triangle, then my angle is going to be the inverse cosine of adjacent over hypotenuse. Okay, and so that gives you a number that I've written down, but I'm going to just do this. It gives you 53.13 degrees. Okay. Oh, and so that is the angle that I want to put up here. All right, so multiply that. Let's see. So I'm going to type into my calculator 490 times 5 times the cosine of 53.13 degrees. Close my parentheses. And you get 1,470 joules. Okay, so that was one option of ways that we could calculate the work. Okay, so that's one way you can do it. Now, the other way you can do it, the second way you can do it, is this. Instead of just using this equation, it's often useful to split your forces up into components. And here I'd be interested in the gravitational force being split up into components. So to calculate the work done by gravity, what I can do is I can multiply my displacement by the component of gravity which is parallel to that displacement. All right? Now in this problem, because it's an inclined plane, this FG parallel is the same as what we usually use as FG parallel, because it's sliding down the ramp. So the displacement's down the ramp, and FG parallel is parallel to the ramp. Okay, so let's make our drawing. So let's see. So So we've got our FG. What we want is our FG parallel, right? Because the FG perpendicular doesn't actually do any work, right? So that's sort of the idea, is that it's this parallel component of gravity that is parallel to the displacement that is actually doing the work. So we got to find our FG parallel. So sticking to our old equations, what we learned was, oh shoot, this is going to be annoying because we've got two different thetas here. Okay. So the theta that I used before is the angle between the force of gravity and the displacement. Yeah, this is why it's so valuable that you understand how these triangles work. All right, so we got to kind of go back to the beginning here. I'm going to actually re-derive the equation for FG parallel. All right, so here's our ramp. So this guy's 5, this guy is 3, this guy is 4. This angle we'd figured out a minute ago was 53.13 degrees. That's what we called theta before. This guy down here is going to be 90 minus that. So that's going to give you 36.87 degrees, right? Okay. So then, here's our object with our force of gravity, which has two components. There is a FG perpendicular and a FG parallel. And so, what's the easiest way to see this? Let's see, so this angle, I'm going to zoom in a little bit. So this angle here is 90 degrees. I happen to know that if this blue angle here is 36 degrees, then this angle here must be the 53 degrees, which means that this is, again, the 36 degrees, right? So let's give that 36 degrees a new name, I guess. We can't use theta, so why don't we call it, I don't know, how about phi or phi? Greek letter phi, however you prefer to say that. All right, so our FG parallel is actually FG times, let's see, parallel is opposite, so that's going to be sine, times the sine of phi. Okay, so let's see, so that's 490 newtons times the sine of 36.87 degrees. So let's grab our calculator and figure out what that is. 490 sine 36.87 is 294 newtons. Okay, and so again, the idea is our original force of gravity goes this way, right? And it has two components. There's the perpendicular component and the parallel component. And it's just the parallel component that actually does work, right? Okay, the perpendicular component doesn't do work. So now to find my work done by gravity, I can take my FG parallel, which we just decided was 294 newtons, down the hill, so I'm going to make it negative, times my displacement, which is 5 meters, down the hill. So multiply that, and it gives you 1,470 1,470 joules. All right, so that was option 2. Okay. Now, despite the fact that that was a pain in the butt, sometimes that's the easier method. Okay, just depending on sort of what you know. All right, now option 3. Let's take a look at option number 3. Clear up my board here. Option number 3. So this time what I'm going to do is, instead of splitting my force of gravity into components, I'm going to split my displacement into components. So I'm going to multiply my force of gravity as a vector times the component of my displacement vector, which is parallel to gravity. All right, so let's go back and look at our original setup. Let's see. So here's my ramp. 5 meters long, 3 meters tall. Here's my block. Force of gravity is 490 newtons down. So check it out. If this is my displacement vector, isn't 3 meters the component of that displacement vector, which is parallel to the displacement? No, try that again. If 5 meters is my displacement, isn't 3 meters the component of my displacement, which is parallel to the force of gravity. Right? Look, these two guys are parallel, right? Force of gravity's down, 3 meters down. Oh, holy cow. So, let's see, my force of gravity is 490 newtons down, negative. The vertical component, the downward component of my displacement is negative 3 meters. Oh my gosh. That was a zillion times easier than method 1 or method 2. All right? So, that is that. All right? So I think that it would be worth your while. I don't want this video to be 7 hours long, but I do think it would be worth your while at some point. And I guess we'll get examples like this on the homework. But I guess just remember that if you want, at some point, you could go back and do example number 4 here. All right? And I've got the answers there for you. All right? So, yeah. Oh, okay. Now, let's talk about network. All right? To calculate the network. So, again, everything I've done so far has been, we've talked about the work done by one force, okay? But sometimes you're interested in the overall work, the network, the total work, all right? And there are 2 ways you can do it. Option 1 is you can calculate the net work by finding the work done by force number 1, the work done by force number 2, the work done by force number 3, etc., and then adding them all up, okay? It turns out you can also, if you figure out what your net force is and treat that as a force, you can calculate the net work by finding the work done by your net force. Okay? So you can calculate your net work by going net force times displacement times the cosine of theta, where theta is the angle between your net force and your displacement vector. Okay? Or you can, find the parallel component of your net force times your displacement. You know what I mean? So you do it the same way, but just with your net force. All right? Now, it turns out there is a fourth way to calculate work. And that's what this last example is going to show us. Okay? So here it says a box is sliding across a frictionless floor. A force F. So I'm going to do everything for my force. I'm going to do that in blue. So it's 3I minus 8J. So here's my force. 3I there's my y component, right? So here's my force vector, okay? Then my displacement vector, we'll do that in red. So the displacement vector is, let's see, negative 4I. I guess it doesn't matter. It doesn't need to be negative 4I. So notice I drew, in the blue drawing, I drew the 8 longer than the 3, right? Because 8 newtons is a little more than twice 3 newtons, okay? I didn't really draw it here. Well, I guess as long as we're going through this. All right, so 8 newtons should be a little more than twice as long. Okay, there we go. All right, now over here I don't have to use the same scale because they're different units, right? These are now meters. Oops. All right, so I'm going to go 4 meters to the left, 2 meters up. So here's my displacement vector. All right, so I guess this is my delta x, and this is my delta y, right? Okay, so now, using our definition of work, I can go, all right, well, work is force times displacement times the cosine of the angle between those two things. So I guess the first thing I need to know is, what is F? Well, F is the magnitude of this hypotenuse here, right? It's the magnitude of my actual force vector. So if you do the Pythagorean theorem, your F ends up being about 8.54 newtons. Okay, so I'm going to put that right here, 8.54 newtons, times my displacement. So now I need to know this guy. So again, use the Pythagorean theorem and find that displacement vector. Turns out to be about 4.47 meters. Times the cosine of the angle between them. Ugh. So remember, to find the angle between them, you have to draw them head to tail. So I'm going to cheat. I'm going to move these guys. All right, and so the angle that I want is So you can find, really it doesn't matter. I'm going to find the smaller angle. I want this angle. Okay, if you wanted to, you could find this angle over here, and it still works. But I usually try to choose the one that's less than 180 instead of the one that's more than 180. All right, so let's see. So how am I going to do this? Let's see. So I guess I could do a little bit of trig and find this angle. I'm going to do that. So if I do a little bit of trig and find that angle there, it turns out to be about 69.4 degrees. Oops. 69.4 degrees, which then means that, oh, I'm so out of colors. This yellow guy here is going to be 90 minus that, right? I know this drawing is cluttered. The whole point of this is that there's an easier way to do it, but I just want to show you that it works. All right, so 90 minus 69.4 is what, 20.6 degrees? Is that right? Yeah. Okay, so that's that. And then this purple chunk here is 90 degrees, right? Because it is. So you've got a vertical and a component, vertical and a horizontal bit there, so that's 90 degrees. All right, and then finally this blue bit here I can find again by doing some SOHCAHTOA on the red triangle. I guess I could have drawn it in red. So this guy I can find using SOHCAHTOA. That turns out to be 26.6 degrees. So then my green angle is 20.6 of yellow plus 90 degrees of purple plus 26.6 degrees of red gives me an angle of 137.2 degrees. That was a lot of work. Times the cosine of 137.2 degrees. So multiply all of this out using your calculatrix, and you get pretty close to negative 28 joules. Okay, and it should make sense that it's negative because you can kind of see that my displacement's kind of this way, right? And my force is kind of working against that. It's not exactly the opposite direction, but it's definitely working against that motion. Okay? All right, so there's my work. Now, here is method number, so we just used method number 1 to do that, right? Here's method number 4. Method number 4. I think we were doing it in purple before. All right, so it turns out, so everything that we're doing here is a dot product, okay? And a dot product is one of two ways that you can multiply vectors. Okay, so there's what's called a dot product and what's called a cross product, okay? When you calculate work, you're using a dot product, okay? So the technical way of writing work is you go, work is the dot product of force and displacement. So this little thing says, hey, you're multiplying these two vectors, but we're going to use what's called a dot product, okay? And so one way of doing it is to do what we were doing before, force times displacement times the cosine of the angle, okay? It turns out, though, the other way you can calculate the dot product is by multiplying your x components, multiply your y components, and then add. So it also turns out that work can be calculated by multiplying fx times delta x, multiply fy by delta y, and add. Okay, but you got to keep track of your positives and negatives. Okay, so for us, holy moly, let's see. So the work is, so I'm going to multiply my x components, I'm going to multiply my y components. So let's see, x components. So here's the horizontal component of my force, here's the horizontal component of my displacement. So that's 3 for my force times negative 4 for my displacement. I guess newtons and meters, right? Plus, we'll do the plus sign in black because you care. All right, and then we'll do this guy in blue. Fy times delta y. So negative 8 times 2. Negative 8 newtons times 2 meters. So what does that give us? Let's see. What is 3 times negative 4? That's negative 12 joules plus negative 8 times 2 is negative 16 joules. Add them together. Holy moly, you get negative 28 joules. That's cool. All right, sooner or later when you get to college or sometime you'll learn about these dot products and why they're useful. That's our first exposure to it. All right, so there are two ways to calculate a dot product. Magnitude of one vector times the magnitude of the other vector times the cosine of the angle between them, or multiply your x's, multiply your y's, and then add. Okay, so that is our fourth and final way to calculate work. Here is option number 4. Work is fx delta x, keep track of your signs, plus fy delta y, keep track of your signs. Okay? Now, how you know which way is easiest? I can't give you a cookie cutter way to do that. It depends on the problem. All right? So that's how you calculate work. Right now, you don't really know what work is. You just know it has to do something with change in energy. We will worry about how the energy changes later. So right now, all you need to focus on is how to calculate work. Here are the 4 ways to do that. Okay? Awesome sauces. Have a good day.